for the rest of the class, I want to talk about the diffraction grating. So let's look at what happens when I have a slit. Now, by now you should be able to yourself know or predict what is going to happen. If I have a slit, a single slit of light, and I have a plane wave incident, if the slit is small enough, on a plane over here, if I look at the intensity distribution, I'm not going to get one sharp region with shadow on either side, but instead I'm going to get something like this. Something like this. If I now have two slits, so let's say I have two slits and I have a plane wave incident, each of these slits will create a pattern like this. Therefore, what I see on a screen now is going to be the combination of those patterns, right? So I might see something like this. And something, okay. As I go on increasing, so I'm sorry, I've drawn this very similar. As I go on increasing the number of slits, I get sharper and sharper peaks, okay. So the more the slits, the sharper the peaks. And so a diffraction grating is nothing but a periodic collection of slits. What plays a role in the output light is the width of each of these apertures and the period, the spacing from one aperture to the next aperture. So these two parameters, W and D, are very important. When light is incident on the grating, so this is a front view of the grating. And now if I were to illuminate the light, okay, and I look at it from this point, that's what you're seeing over here. So the grating exists like this, right? And you're illuminating the light. Because I now have light constructively interfering at select positions, I have a number of what we call orders. One order continues as if there was no grating at all. This is the order that, in a sense, is following the geometric optics rules. And that's why we call this the zeroth order. I may have some orders to this side, I may have some orders to, I may have some orders to this side, and if this is a reflective element, I may have some things to this side, okay? So instead of now you had one incident beam, because of this periodic collection of slits, you now generate a number of beams, but those beams don't take any random direction, they take specific directions according to the width, the period, the wavelength of the light. The incident, this and this period D, so this is what controls it, the lambda, the incident angle, this is theta I or beta I, whatever you want, the incident angle, the wavelength and the period. This controls the different directions the orders will take. So they take very specific directions. I can consider two kinds of elements. I can consider amplitude grating. So I have a periodic collection of slits. That means in certain region light is blocked. So it's blocked over here and it's allowed to pass through in the other region. So it's a transmission element. But you can see straight away this is not a good element because these regions are blocked, so I'm losing half of the light. Right? And you never want to have an element or an optical system where you throw away half of the light. That's what you're doing with an amplitude grating. I could therefore say, let's have a phase grating. I need some periodic structure. I need a structure that repeats but causes a number of beams to form. I can do that by saying, have one set of beams go through an optical or a phase step. So they're now traveling this and this and this and this and this are traveling a different optical path length because of this thickness and this refractive index. And that is what causes the multiple beams to form. Unlike the amplitude case where a blockage is what caused the multiple beams to form. So here you had this beam, you had this beam, you had this beam. And these were blocked. And here you have light coming through everywhere, but this has an optical path length difference. These all have the same optical path length, whereas these are all a different optical path length. And that is what is causing the multiple beams. These are both examples for transmission elements. I could have reflection elements where the optical path length is now, because this light, though both sets are reflected, this is reflected after going through twice this distance. So it goes down and it comes up. So it has traveled twice a distance more than these beams. Okay. So if I take a grating splits up light into number of orders. Those orders could be reflection or transmission depending on the type of grating you're using. And the convention is, if you have light incident on your grating like this, all angles are measured with respect to the normal to the grating. So it's positive if it goes in this direction, the angles are negative if they go in this direction. How do I define the orders? Well, if the beam was incident like this, Snell's law of reflection says the reflected light should go in a certain direction. That's the 0th reflected order. Same as what is expected by Snell's law of reflection. If I look at the refracted, so either I consider my grating to be very thin, so light travels just along a straight path, or I take into account the refraction caused by this grating, and I look at the beam that follows Snell's law of refraction. That is the 0th transmitted order. The other orders are caused by where interference, constructive interference happens between the multiple beams generated by this grating, and we call them the -1 orders or the +1 orders depending on which side of the 0th order they are. So you can see all the orders towards that have to be rotated anti-clockwise to reach the grating. These are the -1 orders over here for transmitted, and these are the +1 orders over here. Okay, so the order number or the order sign rather is determined by the location of the order with respect to the 0th order, and angles in general are defined, or their sign is defined with respect to the grating normal. Okay, so how do we arrive at the grating equation? I have a beam of light that's incident, and now let's just take two extremes of this beam, the one that hits this point and the one that hits a point corresponding to one period away. So this is one period. We're using capital lambda to indicate a period. Now this is a plane wave incident on the grating. So at this place, this is the phase front of the grating, phase front of the plane wave. That means this is constant phase. What happens though is when the wave hits the grating at point A, this reflects and starts to travel along this path, whereas this continues along this path. So the size of this plane wave may change, but it's still a plane wave, and so at some other point I can look at the phase front here, the phase front here, the phase front here. Let's look at the phase front here. That's when this part hits B dash, and by the time this part hits B dash, this has traveled from A to B. So I'm interested at the wavefront at its starting point, A dash, and then at B dash. I want this to be an order of the grating. That means this must correspond to where constructive interference happens. So if I look at the path length difference between these two rays, they must be of some multiple of the wavelength. Now let's assume this medium is N, of refractive index N. That means N1 is equal to N2 is equal to N. So the path length traveled from A dash to B dash, I've put it as N1 here, but it's all the same refractive index. This one has traveled A to B in the same refractive index, so these are both N. And the difference in these path lengths, if it is a multiple of lambda in this region, then I will have constructive interference, and this will correspond. Condition that makes this an order of the grating. When I say it is an order of the grating, I am in effect saying this is where constructive interference happens. So I can rewrite lambda naught by N as lambda, and if you do the geometry of this, if just from trigonometry, this A dash B dash, so you look at this triangle, this corresponds to capital lambda, this is the distance A dash B dash, this is the incident angle beta I. So this angle is beta I, right? And so if I use this trigonometrical construct here, I will arrive at this expression, and this is the standard diffraction grating expression. You will often see it given as d sine theta is equal to m lambda. In that case, they are calling d the period, and this is for normal incidence. So the sine has been absorbed into the index m, and this is for normal incidence. So if I were to make beta I go to 0, then it would reduce to this. So this may be something that you have seen before. D sine theta is equal to m lambda. But the most general form of the diffraction grating is this, where you take into account not just the angles of the orders, which is beta mr, so m corresponds to each order, but beta I, which is the angle of incidence. So this is the beta mr if you consider this to be the mth order. Okay. So this construction tells us when light is incident on a grating, and what is a grating? A collection of periodically spaced slits. They may be amplitude slits, they may be phase slits. When light is incident on such a structure, it breaks up the light and sends it into very specific directions called orders of the grating, and those orders are determined by the period, the incident angle, and the wavelength of the light. Okay. What this equation does not tell us how much of the light goes into the 0th order, how much goes into the 1st order, how much goes into the minus 1st order or the 10th order, the minus 100th order. Do those orders even exist? It just says it's possible to get light into all these different directions with this kind of geometry. So how do we figure out the efficiency? That is, how it's defined for a diffraction grating is how much light went into the 1st order compared to the light that was incident on the grating. Okay? And two things are important here, this height of your grating as well as the ratio of this part, so this structure to the whole structure. So this is called the opening ratio, W by D. Sometimes you see this also as fill factor, W by D. Okay, so how does this help us figure out efficiency? Let's consider a beam that's incident, and we're only now looking at a part of that beam, the path that traveled through this section of the grating. So it went through a height h of refractive index n. So the phase seen by this part of the beam is 2 pi by lambda into nh. The other part of the beam, that is this part, it also would see a phase 2 pi by lambda, but there's no n here because it traveled through air. So the phase difference then between, let's say this is part A of the beam and this is part B of the beam. So the phase difference between parts A and B is going to be the difference between these two. And that's what's given over here. Now I want light to go only into the orders. Now you can imagine, what did I say the 0th order was? The 0th order is the direction light would take if this was a refractive optical element. So I don't want to use that direction. If I wanted that direction, I won't choose a diffractive element. I'll choose a refractive element where all the light goes into that order. It's very efficient. In a diffractive optical element, I want to send light into the orders. That's where it's different from the refractive elements. In other words, I want to minimize the efficiency in the 0th order. And how could I minimize that efficiency? If this phase difference was pi, destructive interference would occur for the 0th order. And if I then use this expression, that is 2 pi by lambda h n minus 1 is equal to pi, and I extract h from this, this is the height the grating has to have in order to ensure no light. That means no light in the 0th order. If the light cannot go in the 0th order, it has to go into the higher orders, and I've made it more efficient that way. Okay? I can use a similar idea for a reflection grating. Here, part A of the beam hits this surface and reflects here, whereas part B travels this distance h and then another distance h and comes here. So the phase difference now between these two is 2 pi by lambda 2h minus 0, because this hasn't, if I consider this as my base, my reference point. Okay? Again, if I set this condition to pi, this is for 0 order cancellation. It reduces to this. So in a reflection grating, if I want to cancel the 0th order, I have to choose the height of the grating to be lambda by 4, whereas in the case of the transmission grating, I had to choose the grating height to be lambda by 2, as well as take into account the refractive index. Why do I have to take into account the refractive index? Think about it. In the transmission grating, as the name suggests, the light is transmitting through the material. It sees this N. Whereas in the reflection grating, we have some reflection coating here. We are just using this material N as a substrate. The light never actually sees the material. And therefore, the refractive index of that material doesn't matter at all. What matters is only this height h. But the principle of how you cancel the zeroth order should be clear for both these cases, and you can apply that even to any other diffractive element you might be designing. Okay, so if we have designed the height of your grating correctly, you have cancelled the zeroth order. That means all the available light, all the incident light is only going into higher orders. But even there, how do I know how much goes into the first, the second, the third, the minus first, the minus second, the minus third? So we need to look at the fill factor or the duty cycle. So let's think of this before we try to do any maths for it. Let's say I took a substrate and I fabricated a grating on top, or I took three different substrates of the same material, and in each case I fabricated a grating. They all had the same period. So you can see this grating 1 and number 2 and number 3. In all cases, the period is the same. This is the period in all cases. But the fill factor is different because the width of this in this case is so small. Here it's really very large, and here it is 50%. So if I take the ratio of W by D, maybe this is something like 10%, maybe this is something like 90%, and here it is 50%. Okay? If you measure or calculate the efficiencies in all of these orders, you will find for a grating with what we call a binary grating, if you study the efficiency in the existing orders, as you change the duty cycle, that is, as you change W by D, right? So what these three graphs show, this is for the first order. Remember, you have chosen the height correctly, so there is no zeroth order. Okay? So it's only the higher orders. And this structure is symmetric. So if there's light incident here, some amount of light goes into the first order and an equal amount goes into the -1 and +1 orders, because this is a completely symmetrical structure. Whatever is satisfied for constructive interference in this side is satisfied for this equal and opposite angle on this side. So if I have 10% light going into this direction, I'll have 10% light going into equal and opposite direction, because this is a symmetric structure. Right? What do I mean by symmetric structure? If you remember the Fresnel prism or the diffractive prism, this is not symmetric. The light comes here, it will preferentially send light into one direction compared to another direction, because the structure is not symmetric with respect to the incident light, whereas this is symmetric. Okay? So in this structure, in these graphs, we are varying the duty cycle and looking at the efficiency in the first order, the second order, and the third order. And you can see at the 50%, the first order has about it's actually 40.5% is the efficiency. There is no second order. The second order has 0% and the third order has less than 5%. This is for a duty cycle of 50%. If I go to some other duty cycle, say 70%, you can see the first order has some efficiency. There is some efficiency in the second order. There is almost nothing in the third order. Now, think about this. If I look at this structure or this structure, that is gratings 1 and 2, If I were to go on reducing the width of grating 1 or increasing the width of grating 2, so say I took this structure and I made it even narrower, so it was something like this. My substrate. It's almost as if I have no grating. Now take this structure and say I make the period like this. It's almost as if I have no grating. This is almost becoming this. And if I look at this, or this, or this, if I have no grating, I don't have orders. The orders come because I create zones, and those zones create beams, and those beams interfere and give me certain preferential directions. But if I remove those beams, as I almost do when the fill factor becomes very small or very large, then I get very little light in orders. And that's what you'll see if you go to duty cycles which are very large, above 90% or less than 10% or even less than 20%, you see that the amount of light that's going into the orders is very small. So definitely 10% or 90% is almost giving me a structure that's not a grating, and that's why there's no efficiency, there's no light here. In that case, all of the light is just following geometric optics. There's no zero order cancellation, because for that to happen, I needed to have a number of beams that could cancel. Here I'm just saying there's one beam, it just goes through that grating as if it sees a slab of glass. Okay? So you can do a lot of funky things with gratings. Gratings are used in spectrometers because, recollect, every expression that we have arrived at has been arrived at for one wavelength. And that means I will get a number, the first order, minus first order. This is for lambda 1. But if I have now a second wavelength incident, maybe that lambda would go here. This is the first order for lambda 2. So this may be M1. This is M1. This is M minus 1 for lambda 1. I might have M1 for lambda 3 and so on. So a grating splits colors, and that's why they're used in spectrometers. But I could also think of doing tunable gratings. I could play around with the period. So I could also play around with the period. And this schematic just shows you, if I had a grating where, in this case, it almost is not like a grating because these gaps are very small, most of the light that's incident is going to reflect off. So it's like it's acting like a mirror here. This grating has less than 10% fill factor. So it's acting like a mirror. And if I could somehow pull down every alternate period, and that's what you see here, suddenly it starts behaving like the diffraction grating, and I have a number of orders. And if I pull it down by the right height, the 0th order would be cancelled. And only these orders would exist. So I could create a tunable grating. Why would I need to do that? Look at an application. Let's go back to spectroscopy. I have a light source. That means I have a range of wavelengths. Those different wavelengths are going through a sample, and from the way the wavelengths change through the sample, so let's say if I looked at intensity versus lambda here, I might have something like this. So all wavelengths exist in almost the same intensity. But after the sample, if I looked at it, so I looked at it here, maybe some wavelengths have been absorbed. From this, I can tell what that sample is or what the concentration of some chemical in that sample is, because say this wavelength was absorbed, this wavelength was absorbed. But in order to do this, in order to generate this intensity versus wavelength graph, I need to be able to measure the value of the intensity at each wavelength. How do I do that? I use a grating. So in this simple schematic, you can see the light comes through the sample, it hits this grating, it's a static grating, and it splits out the different colors. So I need a detector where from the location, so from this pixel, if this pixel has light on it, let's say pixel 1 has light on it, then I know this wavelength is present and I know the intensity of that wavelength. Pixel 2, another wavelength is present, I know the intensity of that wavelength, and from this array, I can then draw a graph like this or arrive at a graph like this. This means I must have a one-dimensional detector which is an array of pixels, and that's quite expensive to have. Instead, could I not use a single photodetector? The problem is, how do I know which wavelength is falling on it? Well, if I change my grating from a static grating to a tunable grating, what happens is when I say tunable, what's being tuned? The period is being tuned. So remember, d sine theta is equal to m lambda. If I'm tuning d such that theta stays constant for different wavelengths, that means I can tune this so that initially the green wavelength is incident on the photodetector, but I tune the grating so that in the next instance, maybe the blue wavelength will be incident. Or I tune the period so that in the next instance, the orange wavelength is incident. So the photodetector, I need now only a single photodetector. It stays in one place, but because I'm changing this parameter, each wavelength in turn is getting imaged onto this photodetector. So here I get the difference then is I get a one-shot measurement. And in this case, I need to take measurement of each wavelength one after the other. Okay, but it makes it more compact, and it could, because for certain wavelength ranges the one-dimensional array is very expensive, so it could even make it cheaper. Okay, so coming to the end almost, and let's just do a quick recap. We started out by saying, since a change of phase of 2 pi doesn't really optically make a difference, can we convert a refractive element to a diffractive element by removing all the unnecessary 2 pi's? And we saw that yes, we can do that, and we'll end up with an element like this, and we do call this diffractive if these dimensions, this height in the order of wavelength. This structure in the middle is still quite hard to fabricate with current technology because it has these curved structures. So what if we did an approximation, and instead of this curved structure, we approximated and said wherever the height is above a certain value, I'll have this as having one height. Wherever it's below a certain value, I'll have the height as 0. And if I do that everywhere, right, so I'm putting a cutoff and saying height above something, make the height 1, height below something, make the height 0, I end up with what is a binary diffractive. Now this serves the purpose, except we should expect differences in behavior because this now is an approximation to the analog element. Okay, and although we looked at this already, let's look at it now with a more critical eye and say what is the problem with a binary diffraction grating. Okay, we always want light elements or devices or systems to be as efficient as possible. So when light is incident, if my goal was to redirect light with the diffraction grating, I always send light into a +1 and a -1 order, or to a +2 and a -2, +3 and a -3. I can't get away from that, and as I pointed out earlier, it is because of the symmetric nature of this particular structure. Okay. How do I get rid of this? Or why exactly does that happen? You could think of this in terms of a Fourier analysis of the grating. So if I gave you a signal like this and I asked you to Fourier analyze this signal, so this is a periodic set of square pulses. It's a nice analogy to help us understand what's going on with the grating. If I thought of this as a periodic set of square pulses, what would the harmonics that are required to create this periodic set of square pulses? And you'll see, if you have a 50% duty cycle, you have a number of harmonics that are present. In fact, all the odd harmonics are present. So you can think of your periodic set of pulses, okay, there's a large number of them, as being the sum of a different set of harmonics of different amplitude, of different frequencies. When I add them up together, they give me this. And if it's a 50% duty cycle, I will only have the odd numbers. So I'll have +1 -1 order, +3 -3 order, +5 -5 order, but not the even numbers. If the duty cycle changes, of course you will have the other orders. And you remember, you can get an idea of that if we go back to this graph. When we did the 50% duty cycle, you can see the second order went to 0%. Whereas if you had a different duty cycle, then all the orders, the first, the second, the third, they all existed. Okay, so a nice way to understand the orders of a grating is just to think of this as light is seeing this structure which is made up of a number of harmonics, and light takes the path corresponding to each harmonic. Okay. If I want to get rid of the problem of having always a +1 and a -1 order, then I have to break the symmetry somehow, and this blazed prism structure would blaze the symmetry. So light incident on this would all bend in one direction, one preferential direction. So you could have like almost 90% of the light going only into one order. I could otherwise convert this to a structure with multi-levels like this, and it turns out if you have 8 levels and above, you can have much greater than 95% efficiency, right? So these are some ways of making a binary element more efficient, but of course there are limitations. You might think, well, I should always do this, but it becomes difficult in terms of fabrication. Okay, so with that, I will wind up the summary of diffractive optics. We've not gone into a mathematical analysis of it, because you can actually spend an entire semester, do an entire course on diffractive optics. What you should have learned in this discussion on diffractive optics is that diffraction is inherent in optical systems, because you have the edges of the optical systems where you can't neglect the size, or you can't assume lambda tends to 0, or you can, and in those cases you consider diffraction a problem and you have to solve it somehow. You can look at it from a different approach and say, since diffraction affects intensity and phase of light, I can create optical elements using diffraction, and we've looked at the grating as one example of how you do that. I should mention two things that I think I forgot to mention. One is, when you're looking at a diffractive element, so you have light incident and you're looking in the region near the element, we call this Fresnel diffraction. And if you're looking in a region far away, it's Fraunhofer diffraction. Okay, and these are the scientists I mentioned right at the beginning, Fresnel and Fraunhofer. And I will end with just some pictures showing you some structures that we have fabricated here. So this is a blazed grating. You can see this scale represents 5 microns. So this is about 10 microns. So that's the size, right? This is actually a grating, a circular grating fabricated on a fiber tip. So this is the diameter of this, it's a fiber. So the diameter is 125 microns. Again, this is roughly 10 micron diameter. And these are some other kinds of elements also fabricated on fiber. So just to show you or give you an overview of what all is possible with the diffractive optics, I want to end with one example, and that is when we do imaging, we talk about diffraction being a problem, but please do look up Professor Stefan Hell. So maybe some of you will remember his name. He won the Nobel Prize in chemistry in 2014 for advances in fluorescent imaging. And you can imagine that in imaging, resolution of your imaging system is always a major issue. And the best systems are diffraction limited. And Stefan Hell used, surprisingly, diffraction. So he used a diffractive element to create a super resolution system. So I'm not going to talk about the system today, but I will urge you to go and read up on that, because it's interesting that he used the idea of diffraction, which normally an imaging person will think is a problem for imaging. He used that to achieve better than a diffraction limited system. And so that's very interesting. Okay, so I hope with that you have a good overview of diffraction and will help you also with the programming exercises that you've been given. Thank you.